In section 7.3, we prove the converse of the channel coding theorem. In the communication system that we are studying, the random variables w, x1, y1, x2, y2, all the way to xn, yn, and w hat are generated in this order. The memorylessness of the DMC imposes the following Markov constraint for each I. Namely, given xi, yi is independent of all the random variables generated before xi, that is w, x1, y1, all the way to xi minus 1, yi minus 1. The dependency graph, which illustrates the Markov constraints of the random variables, can be composed accordingly. We now see how the dependency graph can be constructed. First, as we have mentioned, the random variables involved in this problem are generated according to the following order: w, x1, y1, x2, y2, x3, y3, all the way to xn, yn, and w hat. Let's Q denotes the joint distribution for all the random variables. For such a general distribution Q, it can be factorized as qw times qx1 given w times qy1 given wx1 times qx2 given wx1 y1 times qy2 given wx1 y1 x2. So on and so forth. Such a factorization is valid as long as the conditional events all have non-zero probabilities. Otherwise, the joint's probability is equal to 0. Now, for the conditional distribution qy1 given wx1, by the definition of the DMC, when x1 is given, y1 is independent of w. For the conditional distribution qx2 given wx1 y1, because x2 is a function of w, once w is given, x2 is independent of x1 and y1. For the conditional distribution qy2 given w, x1, y1, and x2, according to the definition of the DMC, once x2 is given, y2 is independent of w, x1, and y1. Accordingly, we have qw times qx1 given w, where qx1 given w correspond to this edge in the dependency graph. So one can think of passing the random variable w through a channel to obtain the random variable x1. Now the conditional distribution qy1 given x1 is just py1 given x1, which is the transition probability of the channel. And this corresponds to this edge in the dependency graph. So we can think of passing x1 through the channel py given x to obtain the random variable y1. Likewise, we have qx2 given w, which corresponds to this edge, and py2 given x2, which corresponds to this edge. Continuing in this fashion, we can construct all the other edges. And this completes the construction of the dependency graph. Thus, there is a one-to-one correspondence between the dependency graph and the Markov structure of the random variables in the problem. We continue to use Q to denote the joint distribution and marginal distributions of all random variables. In the last slide, we have worked out a factorization for the joint distribution Q. More precisely, for all quadruples w, x, y, w hat such that qx is greater than 0 and qy is greater than 0, we have the factorization q w x y w hat equals qw times the product I from 1 up to n q xi given w times the product from I equals 1 up to n p yi given xi times q w hat given y. We have seen how we can construct the dependency graph from this factorization of the joint distribution Q. On the other hand, this factorization can also be obtained directly from the dependency graph. Note that QW is greater than 0 for all W because the message is chosen uniformly, so that QXI given W are well defined. Also note that QXI given W and QW hat given Y are deterministic. The dependency graph suggests the Markov chain W, X, Y, and W hat, and this can be formally justified by invoking proposition 2.9. All we need to note is that the first term QW depends only on W, the second term depends only on W and X, the third term depends only on X and Y, and the last term depends only on Y and W. We are going to prove two propositions that arise from the Markov structure of the problem. The first proposition says that for a sequence x such that qx is greater than 0, qy given x is equal to the product of I from 1 up to n, pyi given xi. This means that the probability of receiving a particular sequence y, given that a particular sequence x is transmitted, is equal to the product of the conditional probabilities for the individual transmissions. The proof goes as follows. First, for all x sequence and y sequence such that qx is greater than 0 and qy greater than 0, we have qxy equals summation w hat qw xy w hat. Applying our factorization for q, w, x, y, and w hat, we obtain this expression. Here, note that in the summation, the first three terms does not depend on w hat. So we can move it outside the summation w hat. Now, summation w hat q w hat given y is equal to 1 because qw hat given y is a conditional distribution. Furthermore, the product of all I, pyi given xi, does not depend on w, and so we can move it outside the summation w. Furthermore, qx can be obtained from qxy by summing over all y, and applying the formula we have obtained for qxy, we have this. Now the expression in the first square bracket does not depend on y, so we can move it outside the summation y. And for the summation y, we write it out explicitly as summation y1, summation y2, all the way to summation yn. Now we claim that summation y1, summation y2, all the way to summation yn, the product of all I, pyi given xi, is equal to the product of all I, summation yi, pyi given xi. We now illustrate this for the case when n is equal to 2. For this case, we have summation y1, summation y2 the product of I from 1 up to 2, Pyi given Xi. Writing out the product, we have summation y1, summation y2, Py1 given x1, Py2 given x2. And then this can be factorized as the product of two summation, because Py1 given x1 does not depend on y2, and Py2 given x2 does not depend on y1. And so we can write this as the product of I from 1 up to 2, summation yi, Pyi given xi. Now for each I, summation yi, Pyi given xi is equal to 1, because Pyi given xi is a conditional distribution. And therefore, we have summation w, qw, the product of I, qxi given w. Therefore, for x such that qx is greater than 0, qy given x is equal to qxy divided by qx. By comparing the two expressions, we find that this cancels with this. And what is left is the product of all I, Pyi given xi. And this proves the proposition. The next proposition we are going to prove is a consequence of the previous proposition, which says that the conditional entropy of the received sequence y given the transmitted sequence x is equal to summation I equals 1 up to n, the conditional entropy of yi given xi. For the proof, we first observe that for any xy pair, if qxy is greater than 0, then qx is greater than 0. Thus, by the above proposition, equation 1 holds. Therefore, by equation 1, we have minus the expectation of log of qy given x is equal to minus expectation of the log of the product of phi equals 1 up to n, Pyi given xi, which is equal to summation I equals 1 up to n minus expectation of log of Pyi given xi. Now minus expectation of log qy given x is simply entropy of y given x, and minus expectation of log Pyi given xi is simply the entropy of yi given xi. So we have proved the assertion that entropy of yi given xi is equal to summation I equals 1 up to n, the entropy of yi given xi.